I would like to welcome everyone to today's webinar, The Ascent, Approving the Climb. My name is Marcy Weber, and I'll be the education team moderator for today's presentation. We have a great panel of experts who worked directly on the project, so you are in for a treat today. The American Wood Council is a registered provider with the American Institute of Architects Continuing Education Systems. If you would like us, if you're an AIA member and would like us to report your credits, send us your membership number at the end. Disclaimer, note that this webinar and associated slides should not be used as a substitute for competent engineering support and expertise. This course is copyrighted and not eligible for reproduction. And here is the team that's providing this course for you today. Our speakers today are our distinguished panel of experts who were involved with the design and approval of the Ascent building. Jason Korb of Korb & Associates, Jason Kump from Thornton Tomasetti, and Chief Eric Roden of the Milwaukee Fire Department. Our engineering moderator is Director of Educational Outreach, Lori Cook, and behind the scenes is Kim Paulson, our Education Administrator, and myself, Manager of Education and Accreditation. So now I'm going to give you over to Jason to begin talking about the Ascent.
Hello, everybody. My name is Jason Korb. I'm an architect and founder of Korb & Associates Architects in Milwaukee, Wisconsin. And myself and my colleagues here are here to speak with you about the Ascent Tower in Milwaukee and the various processes we use to get this project designed, approved, and built. Typically, we start off with what's allowed as of right in most timber construction in the US. Here in Wisconsin, we operate under the IBC 2015. We are allowed up to 85 feet in height and up to 7 stories, 6 stories of timber over a concrete podium. This is another small project we designed for the same developer as Ascent, but it represents what is as of right in most of the US. But then in February of 2022, Intro Cleveland opened up, and it became the first mass timber high-rise approved and built in the US at 9 stories tall. It's 7 stories of timber over a 2-story concrete podium. And for a brief while was the tallest mass timber hybrid building in the US and remains, I believe, the largest by volume in terms of volume of fiber. This is Framework in Portland, Oregon, and it is important because it is the first mass timber building high-rise. It is the first mass timber high-rise building to have been permitted in the US. It's 12 stories of timber. The superstructure is 100% timber above grade, and they use the AMMR language, the Alternative Materials and Methods methodology, to achieve approval under Oregon's building code. The project was permitted, as I said, but it was never constructed due to financial considerations. Until recently, the tallest mass timber hybrid building in North America was Brock Commons in Canada. It's 18 stories, 17 floors of timber over a 1-story podium. Brock Commons achieved approvals through a 100% encapsulation strategy, which means that there is no exposed timber in the building. Until Ascent was complete, the tallest mass timber building in the world was Njorstadnet in Norway, and it is about 280 feet tall, and it is also basically 100% timber above grade with some steel embedded in it. So our project, as proposed, Ascent, ultimately grew from 19 to 25 stories during design and ultimately topped out at 284 feet. Here's a rendering of the building prior to construction. So why did my clients decide to do this? They were initially attracted to mass timber for its aesthetic considerations. This is a photograph of an 8-story timber building in Portland, Oregon called Carbon 12. So our clients were attracted to the aesthetics. They thought it was a differentiator in a crowded market. Just a few more shots here. So really attracted to the beauty of the material. But then the more we sort of dove into it, we all came to understand the sustainability benefits of mass timber. And so that just became an extra driver to pursue this construction type. So these are just some facts about the amount of carbon we are sequestering and the amount of time it takes to renew the amount of fiber that goes into the building through natural growth. The statistic that really gets people's attention is here at the bottom, where it's the sequestration is equivalent to taking about 2,400 cars off the road for a year. That carbon will remain sequestered until such time as the wood is allowed to rot or burn, which hopefully won't happen. Here's our site on the north edge of downtown Milwaukee, on a street called Kilbourne Avenue, one of the nicer streets on the north edge of downtown. It's highlighted in purple. The site was home to an Italian restaurant that had been closed for approximately 10 years and was very underutilized on this very desirable street. And then in the background, you can see our Lake Michigan. So the building does have substantial lake views. And here we have inserted the building into its context. So you can see it fits in nicely with the other residential high-rises in the neighborhood and really completes an important corner on the street. The building is 19 stories of timber over a 6-story concrete podium. The cores, one is the main core is stairs and 3 elevators. The secondary core is the second fire stair. Those cores are concrete all the way to the 25th floor. They provide all the lateral stability in the building, but all of the gravity loads above the 6th floor are handled by the mass timber. We did pursue an alternative means and materials path to approval, and we worked with the city of Milwaukee to achieve that approval. We'll talk about the details of that in a moment. So the alternative means and methods path to approval requires independent testing from independent third party. In our case, we needed to perform the world's first 3-hour fire test on a glulam column. We were fortunate in that just 90 miles west of us is the USDA's Forest Products Lab in Madison, Wisconsin. And so they offered to perform the tests, which were conducted in December of 2019 through January of 2020. You can see the burn chamber on the left. On the right is a glulam sample. If you look carefully, you can see the engineers at FPL have sawn the sample in half. They have embedded sensors at various depths in the member. They glued it back together, and then they placed it into the burn chamber. On the left is a photo from the window of the burn chamber during one of the tests that we witnessed. On the right are the 3 completed burn samples. We performed 3 tests across 3 different species for a total of 9. The engineers conduct the burn test. They scrape the char off, and then if you look carefully, you can see the columns have been cut into sections when they then analyze if enough cross-section is still available to make the column structurally viable. All 3 species performed very well, and their burn profiles were a little different, but at the end, they performed about the same and better than the prescriptive rate of the code. The final test that we did was what's called a PRG 320 test, because our cross-laminated timber floor slabs came to us from Europe, and European testing standards are slightly different. That test was completed in March of 2020, and the CLT passed. Here we are, a typical floor plan, so it's an L-shaped building. More interestingly, though, is the drawing on the left, which is the ceiling plan. So anything that is gray has a drywall soffit for a finished ceiling, and anything that is tan is exposed mass timber. So you can see that basically the entire perimeter of the building, including all living rooms and bedrooms, are exposed timber. One consideration that we did have to deal with was moisture getting into the building, and anything you see in this diagram that is red represents potential dew point encroaching into the timber slab, which is not desirable, obviously. Even though we have an AVB and insulation of 2 of the 5 plies, the end grain is exposed. So this is the original model. We worked with Arup out of New York as our facade engineer, and through an iterative process, we redesigned some of the mullion dies to keep that dew point well and truly out of the timber assembly. And so this was the window wall system that ultimately was constructed at Ascent, and you can see how far away from the timber that dew point is. Other considerations, as part of our negotiation with the city of Milwaukee, you'll note in some of these typical details that any area that is outside of sprinkler coverage is protected with a layer of drywall. Most notably, it's outboard of the beams where we can't really get sprinkler heads back there. The other consideration is in the center drawing, we used a window wall system because it is well suited to helping us avoid a chimney effect, which is a real concern in high-rise buildings. And on the bottom, you see some of the smoke index that these materials carry. A commitment we made to the city of Milwaukee was that the entire exterior envelope of this building be non-combustible. We went through, during design, a total of 64 MEP coordination meetings. So the building has an entirely digital twin that was then fed into the CNC machines at the manufacturing site in Austria. So of the thousands and thousands of penetrations in the building, 99.99% of them were successfully located and field drilled. I'm sorry, 99.9% were successfully located and drilled in the shop. There were a few that got missed, but maybe out of thousands of penetrations, we had to field drill maybe 5. So this was a very intense effort, but ultimately very successful. So the second round of VD&C, which is virtual design and coordination, was around the actual structure of the mass timber. An interesting problem or challenge the team ran into was the fact that, or was due to the fact that the timber columns in particular continued to get smaller as the building went up. However, the hardware remained the same. So near the top of the building, it was becoming increasingly difficult to have the fastener screws not conflict with each other. It got very tight at the top, but ultimately we made it work. This slide discusses the timeline of how we got this project put together. We started talking with our client about mass timber in late 2017. By the spring of 2018, they directed us to start looking at this as a possibility for their site. And we immediately put together a presentation. We went directly to the DNS commissioner in Milwaukee. That's the Department of Neighborhood Services. The commissioner is the supervisor of all plan examiners and all building inspectors. As luck would have it, our commissioner at the time, Preston Cole, had a background in forestry. He was familiar with the technology, and he didn't give us a blank check, if you will, but he did instruct his staff to work with us to see if there was a path to approval. And we started those meetings in the summer of 2018. The project was unveiled in the fall of that year, and we immediately then started working with the Milwaukee Fire Department that fall to get their input on how to make this building as safe as possible from a firefighting perspective. As again, luck played a role here. Chief Roden, who's on this presentation, was already an early thought leader in firefighting circles around mass timber, and the Milwaukee Fire Department just became a great partner in this process. So we did apply for a footings and foundation permit and 3 variances in February of 2020. We had our final conference with city staff in May of that year, and all permits were issued at the end of July. Construction started in August of that year, and the project was completed just last summer. A few photos during construction. So here we see the raw timber in the early stages of timber installation. If you look carefully, you can see all of the penetrations are already in place. So the larger ones are plumbing. You see a few penetrations in glulam beams. Those are fire protection. And that coordination became so important just because you can see we wanted to minimize the soffits wherever possible, which meant that a lot of the MEP systems were very tightly packed into these spaces. This is the kitchen in a 2-bedroom unit under construction. And here you finally see the finished product. So every effort was made to make sure that the timber was completely unobstructed by any MEP systems. Everything is handled from the drywall soffit, in this case above the kitchen. So fire protection, air distribution, and plumbing from the kitchen above. The 25th floor of this building is a resident amenity level. So you can see some of the shared spaces that the residents get to enjoy. This is a lounge with a demonstration kitchen. There are 2 roof decks and this west-facing lounge with very tall timber ceilings. Near the bottom, this is on the 7th floor, is a fitness center. Here the timber members are at their largest. So you can see on the left a timber column that is about 43 inches wide. They get substantially smaller as you go up, but you can see how large the timber gets. This has got 18 floors of load on top of it. And then here's an image of the finished building from just this fall.
Hello, everyone. My name is Jordan Komp. I'm an associate principal and the Milwaukee office director here at Thornton Tomasetti. I appreciate you guys having and listening to me today. For my portion of the project, I'm going to discuss the design principles and construction procedures and process that was utilized for the Ascent building. And so really just talking about the structure and sort of what went into the design and how that coordinated with the construction process on site. So I'm sure, as Jason mentioned, for some of these things, we're 19 stories of mass timber over a 16-story podium, approximately 284 feet tall. And we were sort of approved under the Wisconsin Commercial Building Code, which is very similar to IBC 2015. And we utilized the alternate materials design methods section, and our fire rating and resistance was achieved primarily through a combination of encapsulation and a sacrificial char layer, with about 50% of our mass timber being exposed. High level for the structural system, we have a reinforced concrete post-tensioned podium structure for the parking levels at the base. We have glulam beams and columns up the height for the superstructure, and a CLT slab for the floor framing, with reinforced concrete core walls up the height, which I'm sure Eric will discuss during his portion of the presentation. In terms of structure, as I'm sure you're aware, mass timber is significantly lighter than its concrete counterpart. So one of the benefits was, from a foundation perspective, your foundations can be slightly lighter. In addition to that, for this specific project, we did additional load testing to significantly increase the capacity of the piles and the foundations we were utilizing. What's interesting is actually we were limited not by the geotechnical capacity, but actually by that reaction frame you see there. So that was what limited what the value we could actually test to. And definitely worth noting that these piles, because we actually tested them versus using sort of the standard IBC capacities, we were able to nearly double the capacity, same pile, same material, but just by testing, double the capacity of these piles. As we move up the height of the structure, on the bottom right here, you would have our typical parking level, which I believe is between a 7.5 inch post-tension 2-way parking slab. And then as you see in the upper left, this is really when we start to marry the 2 systems. So the concrete structure versus the mass timber structure. As you can imagine, the column grid for a mass timber building is not the same as a column grid for a parking structure where you need the large drive aisles below. So what we utilized is we had an amenity level where we already had space for this mechanical alcove, and in the upper left there you see a pool structure. So utilizing the depth we already had, which I think for this building was up to 7 feet in areas, we were able to utilize some post-tension transfer beams. I think our beams were anywhere from 42 to roughly 66 inches deep, so 4.5 to 5.5 feet deep. And we used actually a stage stressing because the mass timber was so light that a majority of the weight of the structure actually was which we'll get into in a minute here, is the topping slab on top of the mass timber. So we actually had to stress it in 2 different sequences to make sure we didn't overstress the beam so that you'd see cracking on the top of the slab. And so the primary portion of what we're here to talk about today, this is a typical mass timber floor. So what you have is we have a roughly a 5-ply, roughly 7-inch thick CLT floor slab spanning one way, even though I think everyone knows CLT is a 2-way spanning system. It's primarily typically a 1-way span. And so those spans ranged anywhere from, on average, say 16/8 upwards of 20 feet spanning for the CLT to glulam beams, which typically span sort of on a skip grid, as you can see sort of around those balcony cutouts, anywhere from 20 to 25 feet. And those then spanning to our glulam columns at the corners and at the perimeter. And those glulam columns were shaped also to allow for sort of architectural features, but also with this idea that we'll get into a little later of this char method. And then you can also see on this presentation that we had the reinforced concrete core walls, which were part of the lateral system. And they were actually designed such that from a construction method, they could be cast the full height of the tower without any of the CLT or any of the mass timber acting as diaphragm. In addition to sort of the structural uses of the CLT, or excuse me, of the concrete cores, this was also a discussion that I'm sure Eric will get into in terms of, as part of the variance process, we went through utilizing a reinforced concrete core or lateral system. In terms of the actual connectors, so we talked about the members, we utilized really there's many different connectors, but 2 primary connectors on the job. What you see here is whenever we had an exposed connector, meaning beams and structure that was going to be exposed, we utilized what we call a framework connector based on a job that was done, or some research that was done, I should say, in Portland, Oregon, and I'll get into that a little bit later. But this idea of sort of having this shelf angle out of steel with a knife plate that then it gets recessed into the beams in the field, and then with the blocking below, so that the mass timber is actually protecting the steel element in the connection, and this was previously tested. Next, you have the much more simplified concealed connector, where we're going to have drywall that sort of encapsulates the column. And this connection was used really wherever possible, just because of the efficiencies and sort of the minimum hardware needed. So from a financial perspective, utilizing this type of connector. What you see here, hopefully, is a construction sequence video real quickly, just so you can sort of see the structure in 3 dimensions come together. At the base, you have these 16-inch concrete filled steel pipe piles that were driven approximately 150 feet into the ground. You can see the PT parking structure being constructed, followed by this transfer level I discussed. And then you can really just start to see the parts and pieces. So the glulam beams and columns being set into place, followed by the CLT diaphragm. And it's worth noting that because the CLT was our diaphragm, once the diaphragm was set in place and engaged into the core, they could really remove all of the bracing and the shoring and things that were required, which sort of, if you did standard PT construction, sort of tend to live for a bit longer and maybe impede some of the mechanical and the trades that would have to occur below the level. So if things to consider maybe that are a little different on Ascent or mass timber in general, obviously this idea of the material you're using. So I'm sure everyone's aware that the different species of wood all have different visual appearances, right? Sort of a whiter spruce to a red Douglas fir or a yellow southern pine, but also those appearances definitely play into the material properties, right? Whereas with concrete, it's you know, the strength is not necessarily visible in the color. It was one thing to work with ownership to understand what species they wanted, because it had a direct impact sort of on the strength and the capacities we'd be able to get as a structure. The other unique thing is sort of this design methodology. So what we ended up doing for Ascent was we got all of our wood from overseas in Europe. And as a result, all the European species and grades are sort of graded and processed to a different standard, in this case, the Eurocode standards. So as a design team on Ascent, we actually had to do 3 separate designs. We had to do a NDS or a US code compliant design. We had to do a Eurocode design for the species in their own code. And then we did a hybrid design to verify compliance, where we sort of took those parameters, we brought them into the US code and sort of converted them into what we thought was the appropriate design, all to make sure that we were code compliant with IBC, which is what was used in the Wisconsin Commercial Building Code. So other things that other people I'm sure are well aware of is this idea of with mass timber, that the sound and vibration considerations, because it is so much less dense than concrete. These are things that definitely need to be taken into consideration. I'm sure Jason touched on sort of some of these floor assemblies and the idea of utilizing these 2 to 2.5 inches of gypcrete, one from a fire protection standpoint, but also primarily from a sound and an acoustical perspective, as well as the acoustical sound mats and things that are included. And we also did a vibrational analysis, similar to something you might do at a high-end office building with a composite steel structure when you're trying to push the limits we did a high-end vibration analysis for the Ascent structure. One thing that maybe is not, people don't think about necessarily, but now with this idea of this new tall mass timber, is the idea of vertical compensation in surveying, something that's really common in other materials. For example, for concrete, if you did a tall building, typically you have a schedule because you understand over time the building is going to shrink over time and creep. And so what we did with this project is we set up sort of a robust surveying and shimming program such that we could predict over time the anticipated shortening of all of these columns and sort of give them the allowance in the field to utilize shims to make up for this compensation, while at the same time allowing us in real time to get data and feedback from the contractor. It's worth noting, sort of based on our research and what we saw in the field, we anticipated approximately 2 to 3 times the shortening of this mass timber structure versus what you would maybe anticipate in a reinforced concrete structure. And also what we've probably talked about and people have seen quite a bit is this idea of modeling with the mass timber and how critical it was, not just from a structure where you can see in the left there to make sure there are no things that conflict, screws and it's very tight clearances, but also from a mechanical and the idea that all the trades have to work together, and particularly on Ascent where our materials came from Germany and it was critical, or Austria, excuse me, it was very critical that everything was done in the shop. So when it came to the field, we couldn't simply go to a Home Depot to get a new panel or a new beam. So it was absolutely critical that everything was done right and all the penetrations were coordinated and they came prefabricated in the materials. The other thing that I'll definitely get into a little later here is this idea of fire performance and for the mass timber and how this sort of married into the process of us getting permitted for Ascent. So with that, we utilized the alternate materials provisions of IBC, and the concept that the code was not necessarily trying to limit the use of any materials, but really specifically trying to show the authority having jurisdiction that we were going to provide sort of equivalent performance, whether that's quality, strength, durability, safety. Primarily in this case, we're going to be talking about fire resistance. As a side note, the Wisconsin Commercial Building Code sort of rearranges some of the parts of IBC 2015, which is what this was based off, but they have a very similar, as you can see, their highlighted portion for sort of a very similar language for alternate materials. As part of the variance process, we were approved as a type 4 heavy timber structure, keeping in mind this was before IBC 2021. But as a part of this, we were required to provide a fire resistance rating similar to that of a type 1A structure, with all the allowances to go to type 1B that are similar to any other high-rise structure. So primarily that meant for us a 3-hour rating for our columns and a 2-hour rating for our beams and CLT slabs. To achieve this, there's a lot of different ways you can get to these ratings. You can encapsulate the structure. You can also consider this idea of a char method, which is specified in NDS. So you can do that via calculations. You can have specific tests, sort of full-scale tests that you can see there for the connection, or you can do it based on additional testing. For example, all of the current data in NDS are for up to 2 hours of charring. And this isn't necessarily because something happens after 2 hours, but just simply before Ascent, there was no reason to have testing beyond 2 hours. So as part of the Ascent variance, we actually tested a column for 3 hours to confirm what you can see there is the char depth, in fact, is either linear or less than, so that the rate of char over time actually slows down based on the equations that you would see in NDS. And what that meant for us is sort of for most of our beams, we sort of utilized the char method in this calculation approach. For the columns, as I mentioned, we did the char method, but also this additional 3-hour column testing. Then for the CLT, we actually sort of had additional tests from the manufacturer for those, as well as the char method and the calculations we did ourselves. In addition to what I'm going to get into here is for the fire rating for the connections, there was actually full-scale testing. So I mentioned that we call this the framework connector. That's because a project in Portland, Oregon called Framework got federal funding for their project. And as part of that, they used a similar approach to permitting with this alternate materials method and actually completed some testing for this connector. So full-scale load testing for the 2 hours. And that's sort of what you see from these photos here, in which they confirmed that this connection, or one very similar to it, could maintain the 2-hour fire rating, which would be required by our variance and code. Additionally, I'm sure Jason mentioned, but also Eric's going to talk about a lot of the other requirements that were maybe not structural as part of this variance process. The other one worth noting is unique to Wisconsin. There are no technically special inspections, but due to the unique nature of the project, In addition to being the project manager, I also served as the special inspector for the mass timber frame on this project. So Thornton Tomasetti had people out on site working with the contractor, which was a fabulous experience to sort of solve problems in real time and make sure we're working with them and making sure that it was getting built appropriately for the variance for the superstructure that we had agreed to. Just a few photos here. As you can see the structure going up. Really, it took approximately 6 months to go from start of mass timber to topping out of mass timber there. You see the pictures from June, September, and all the way through December. In terms of components, to simplify, we had glulam columns, you see there on the left, glulam beams, CLT panels, and then these timber screws, which it's sort of, you can see in the picture there, we call them screws, but they're maybe not the ones you typically would think of if you went to like a Menards or a Lowe's. They're really, in some cases, I think we had up to 36 inches deep screws. So really they're quite a bit of work. And if you talk to some of the contractors, they'll tell you stories about how, you know, with a battery powered drill, they could only drill 2 screws before they'd have to recharge a battery. So maybe a little different than you're accustomed to when you're talking about timber screws. In terms of those connectors, we sort of had a couple different ones for the columns, similar to how we had a different connector for exposed and concealed. We had a similar connector, which we typically used at the perimeter when it was exposed. So we utilized an epoxy product where they would set the epoxy in the hole. They would utilize the tower crane to raise up the column, and they would just march their way down there, setting the column one by one before bracing it. The next picture there to the right is a more typical interior connector where there's not as much potential for either any kind of differential loading or unbalanced loading. And then as you keep moving across, you can see the beam, the column, the typical hanger connection. You can sort of see the simplicity and the beauty of the connector where the steel material actually came all the way from overseas. And in the site, they simply sort of have to set the beam, they set it on the ledge, and they literally install 2 screws. And so from a fabrication and a sort of implementation in the field, it really simplifies the time required to set these connections, with all the right being the most simplified connector where it's just a simple bearing connection. We also had in the upper right there some core connections, and I'm sure as everyone's aware, CLT or mass timber and concrete move differently over time. So what we had is, you can see some slots, and they're trying to give the contractor as much as possible, either through the slots or through post-installing the connectors, the ability to give some flexibility with where those connectors lived on the core, because that was done ahead of time, and sort of marrying it to the mass timber elevations as you move up the height. Sort of a picture of this in progress as they're starting to set the CLT for the floor above. You can really start to get a vision for what this exposed mass timber structure could look like. This is a typical floor, with this next photo being the upper amenity level, where I believe the ceiling was 20 to 25 feet. I'll have to check, but somewhere around there. You can also see that there's sort of those connectors we didn't talk about, but those holes were, because the mass timber is so light, we had to consider the idea of this being a 30-story structure, the uplift winds at the top of it, and this idea of needing a bit more of a robust connection to actually drag that force down into the structure, which in some cases meant we needed to take that tension force, you know, down 2 or 3 floors before we got an actual enough weight in the structure to hold this down for potential code uplift wind loads. Also worth noting, just in leaving and sort of leaving you with something, this idea of that everything I talked about here was sort of IBC 2015, which was what our project was more or less approved underneath. The idea that everyone is also aware that IBC 2021 sort of and beyond have created these new conditions of different types of construction. Important to note again, though, that even had IBC 2021 been around during Ascent, it still would have required a variance due to the sort of exposure and the idea of being above 18 stories. And just this idea is that the industry continues to get more research. We'll definitely get improvements and sort of a better understanding of, you know, the code requirements for encapsulation and that sort of thing. So I would highly encourage anyone that's utilizing mass timber to also look into the IBC 2024 preliminarily approved code, just to sort of get an understanding of sort of where the industry is heading. And with that, I thank everyone, and I will pass this on to Eric to complete the presentation.
Hello, thank you everyone. My name is Eric Roden. I am a Deputy Chief with the City of Milwaukee Fire Department. Thank you for allowing me to discuss the Milwaukee Fire Department's involvement in the Ascent project. I'll start off by saying that a lot of people listening and or looking at this project from the outside would view that the fire department would be the greatest obstacle to overcome in a project of this size, scope, and magnitude. However, I'm here to say that is actually not the case, or wasn't the case, I should say, and a tremendous collaboration was developed amongst all parties to get this technology and this building construction method and this type of building built and shown to the entire world. So we were very excited to be a part of this process. I'll get into that story in a bit here, but I first wanted to discuss the fire service's love-hate with wood and delve into a related side in terms of how we fight fires in these types of buildings and give kind of a basic or general overview of some things for developers, architects, engineers, et cetera, to consider when approaching the fire department and kind of understanding what the fire department is looking for and some of the wants that they will have with these types of projects. So I'll start off by discussing, that the MFD met the Ascent team after it was pitched to the city in the, hey, what do you think about an IBC exceeding CLT high-rise building in downtown Milwaukee phase? Now, this is actually a departure from conventional fire department involving and planning because most cities usually reserve fire department requests for subject matter expertise, agency opinion on specific fire protection systems questions and or access concerns. Newland, the developers and Corp architects actually asked us to the table right away for obvious reasons. And this allowed for the most collaborative effort that I have been involved with in my time doing plan review. So I'll get to the Cinderella story in a bit because I first wanted to delve into the fire service's love-hate relationship with wood and how at the end of the day, you as a fire chief or a resident can feel confident renting a top floor apartment in a mass timber high-rise building. Now, when you enter the fire academy day one as a firefighter, one of the first things that you'll be taught is building construction principles and practices. You will receive the narrative fallacy of wood is bad, don't trust the trust, if one trust fails, they all fail, etc. And this has been pervasive in the fire service due to resulting hyperbole after many after-action reviews following some tragic fires and anecdotes from some naive investigators. Obviously, the fire service has fought countless fires in wood structures with legacy-type pre-World War II structures and dwellings holding up the most, or the best. This is due to the switch to more cost-effective, lightweight building construction methods popularized after the 60s, such as gusset plates and TGI beams, etc. The latter being the culprit for a lot of this contempt for wood, as they have been the cause of some catastrophic floor collapses, some of the more recent firefighter line of duty deaths. Although they are designed and tested for tension and compression, they do readily fail under advanced fire conditions. Type 4, or heavy timber construction, on the other hand, gets the fair shake of them all, as many urban firefighters have extensive experience with these buildings. Some, including myself, can discuss responding to massive fires in these buildings, sometimes more than one in the same building, and seeing the building redeveloped or reoccupied only a short time later. This is due to the inherent fire resistance of the 8x8 or 12x12 plus surface area of its load-bearing columns and beams. In fact, a historic heavy timber constructed church in downtown Milwaukee suffered a massive fire a couple of years ago, similar to Notre Dame, actually. And like that, historic renovation is essentially just needing affected columns and beams replaced or repaired and is already back in business. Regardless, wood burns more than steel, so there's a cognitive and empirical bias with wood, especially when a historical Type 4 construction method we thought was replaced by steel and concrete undergoes a renaissance and return to favor. Moreover, when this renaissance is on such a grandiose scale as the Ascent, it surely gives the fire service epistemic pause. And this is where the seminal question was asked by a lot of Milwaukee firefighters when this was posed to the rank and file, is why do they want to build a 25-story piece of wood downtown? Now, as you can see in this slide here, the Ascent is not just a 25-story piece of wood. Rather, it's over-engineered, rated, and tested wood columns and floors on a concrete platform. To put it simply, although much of the structure has been exposed, or has exposed CLT, I should say, when describing it to firefighters, it should be referred to as a hybrid Type 4 to use layman terms. As you can see in the slide, the elevators and stairwells are constructed of reinforced concrete, and the structure has rated gypcrete or drywall in the public hallways. It's sprinkler and has requisite fire department connections and standpipes for NFPA 13 and 14 respectively, and pretty much everything a fire department wants. So let's just discuss some of these wants here. Fire departments just need a few simple things to fight fires in these high-rise buildings. We're looking for protected stairwells to operate from and out of, elevators that we can place under firefighter control, phase 1 and 2, standpipes and sprinklers, HVAC systems to move smoke around, and The Ascent apartments each have their own individual HVAC systems, but we're still able to control their environments and allow us to move smoke in and out of these apartments. We're looking for FDCs or fire department connections to feed water into the building from fire hydrants and alarm systems to let us know where the fires actually are in these buildings. So when discussing high-rise firefighting practices in this building or any other type of building, perhaps the most favored fire protection variable when considering a project of CLT and or a hybrid CLT and concrete is that, or any concerns about mass timber versus steel and concrete for high-rise, is that fire departments will be fighting fires in new mass timber buildings the exact same way, regardless of which of the three little pigs construction types the Big Bad Wolf Fire Department shows up at. Essentially, we're doing everything the same because they're laid out the same, essentially. So with that, we will always launch firefighting operations from the floor below the fire floor, the floor that's on fire, in the stairwell, and use that as our beachhead. We'll designate which stairwell we'll be using to evacuate fleeing occupants or evacuated occupants, and use the other stairwell or stairwell to connect our hose lines to the standpipe system to begin attacking the fire from the floor below. We'll take a look at the annunciator panel in the fire control center in the lobby to see what floor and or apartment is on fire, and then gain and use control of the elevators and stairwells to get up there. Once the fire area and fire department is located and defined, we'll begin dividing the building geographically into operational priorities, with the fire floor and floor directly above being the most important and critical in the first few minutes. We'll then focus on the top floor down until we have searched every floor and stairwell for any possible victims. So let's get to the story here that we're here to talk about today. The MFD, like I mentioned, was asked to be part of the Ascent project during its inception, in terms of notifying the City of Milwaukee of its intent to design and build. The City of Milwaukee's Department of Neighborhood Services was fortunate to have air support in terms of the Chief of Department, Aaron Lipsky, and myself with my involvement as an advisory board member of Underwriters Laboratories Firefighter Safety Research Institute. Coincidentally, UL at that time had recently conducted some bird testing of their own in their Building 11 in Northbrook, Illinois, on cross-laminated timber and mass timber. So I was fortunate to be well versed on and aware of char rates, CLT connections in design, and other inherent fire behavioral concerns of this type of construction. As such, the Ascent team from day one had the necessary de facto subject matter expertise in terms of being able to immediately collaborate with a municipal team that already understood how CLT behaved in fires and what the IBC recommended for fire safety and construction demands, and what we would be asking for when we showed up. Furthermore, I think to save the city and developers time in getting approvals and buy-in to enter into the long variance process that we're discussing here today, and in essence, the alarmism wasn't there that I'm sure a lot of interested parties consider or worry about on the fire side that is inherent in other cities, to go back to that seminal question of why would we design a large building made of wood in a dense urban area, right? The MFD came to the table on what anyone in city planning and permitting would consider day one, so we were able to ask for everything in the IBC that any fire department would want: site security and debris management, working standpipes as it was being built at intervals, sealing completed floors at requisite intervals, etc. The developers and the MFD were able to mutually agree on the nuts and bolts at the start of this collaboration, and it never lost steam from this day forward. As the projects progressed, so did the size and scope of the building. The IBC, agreed upon by the city and developers, capped these structures at 18 stories, so the developers needed to enter into the variance stage to build it higher. The developers, of course, included the MFD, and proof of concept and performance testing required to get these variances, I should say, and its structural members to attain these variances, and invited us to Forest Products Labs in Madison, Wisconsin, to actually see their CLT members on fire. Personally, I can't think of any other time that I've ever been invited to see product development or proprietary building development for the building trades components. So that was a very similar moment as well for the fire service. So to end the aforementioned Cinderella story, the developers made sure the glass slipper fit every time the city and MFD asked to try it on. And I was very proud to be a part of this collaboration. I truly feel that this collaboration is the winning recipe for any type of building development, as no one was left out and feeling like they were being, quote, filled in on what everyone else was doing or thinking after it was already decided. and there were no political back channels to influence anybody or sway anyone's opinion. Everything was out there in the open, and everybody discussed everything. It was amazing. And although the fire department should never stand in the way of economic development, it should always have a seat at the table at the beginning to plan and develop operations to protect these projects. A lot of times, technologies move faster than the speed of academics and experience in fire departments. So we were fortunate to again be well versed and have insight as to every component, how it was built and designed, et cetera. And like I said, in the end, this innovative and unique building was built by a private and public city, not just its developers and iron workers. I think that's pretty cool, and so should everyone involved in this project and anyone listening to this today. The CLT in the end performed as desired by all, and any fire chief should feel confident renting a top floor apartment in the Ascent. It's an amazing building. It performs exactly as it's designed and tested, and that's really everything a fire department can ask for. So with that, thanks for allowing me to speak on behalf of the fire department, and I look forward to any questions that you may have. Thank you.
All right. Thank you to our panelists. Well, we had quite a few questions come in. Thank you to everybody for your questions while we were having the presentation. And if you have other questions, feel free to submit them as we go along. We will do our best to try to get to as many as we can, and we'll hopefully get to all the important points for today. All right, so this first question is for all of you. It's related to the pre-construction planning and the coordination, and I know a lot of you talked about it briefly in your presentations, but can you talk about how important was this pre-construction planning, this pre-construction coordination between the design team, between ownership and the fire and building code officials, the authorities having jurisdiction? And maybe we can have Jason start. Yeah, thank you.
Yeah, so it was absolutely critical because, as I think Jordan mentioned, these, and we both mentioned, these panels in columns and beams were all pre-drilled in a factory, in our case in Austria, and the precision of those CNC machines is something like down to 3 millimeters. So basically, there were two tracks of coordination going on. So in our case, all of the engineering teams, so structural, mechanical, electrical, plumbing, fire protection, that was one path where in our case, the Revit model was just constantly being updated across all engineering disciplines. The second coordination path was done as a subcontract by a company called CAD Makers in Vancouver. So they built the digital twin of the structure and the connectors that Jordan referenced. So there were two separate paths. But as Jordan mentioned, the fact that all of the structural coordination was done digitally meant that, for instance, the columns could show up with their bottom plates already attached and with their framework connectors already in place. And the result of all of this structurally was that once the installers got the hang of sort of how to put CLT together, they were doing a 17,000 foot floor every 5.5 days. So there was a tremendous speed advantage. And by the way, that's with a quarter of the crew that would be on the deck on a concrete building.
Great. Jordan or Eric? Jordan, would you like to chime in next? And then maybe Eric, you can provide your thoughts after him.
Sure, yeah, and I'll segue maybe into probably some of the things that Eric's going to talk about. But to Jason's point, he talks about a lot of the technical aspects, but really from just a project aspect, something like this is really just collaboration is sort of the name of the game, and it's absolutely critical that from the start that everyone is sort of rowing in the same direction, and whether it's ownership or the architect or the engineers or the contractor or the fire department in the city, you know, Jason has mentioned numerous times, if you heard him speak on this, that this project would have been dead, you know, from the start had the city or the fire department said no, we wouldn't have had a project. So that was why, you know, Jason was so adamant that from the start, everyone was brought on board and that everyone was moving in the same direction, because it is such a unique project that it was really critical that everyone was, you know, moving in the same direction and honestly willing to sort of, you know, explore different options, and sort of no one got offended when there was a different position that needed to be taken or that were additional studies. You know, we probably reviewed 7, 8, 9, 10 different structural systems, you know, NLT, DLT, CLT, different directions, different materials, different species, different countries. But it really took a special team to make sure that they were comfortable, and like everyone, you know, sort of persisted through. And then as Eric mentioned, it was such a fantastic job working with the city and the fire department. And it absolutely wasn't sort of what people would imagine with them sort of being prohibited, but really it was a collaborative process to make sure that everyone was moving in the same direction.
Great.
Okay.
And Eric, yeah, thank you. Go ahead.
Hey, good afternoon, everyone. Yeah, I mean, to echo, you know, their sentiment, and to kind of go back to my presentation, I really think it was the winning recipe, due to the fact that, you know, we consider that day one. Obviously, it was, you know, months or if not almost a year into the process of the conceptualization of the project, where we were brought in to sit down at the table. But for the fire department, that's considered day one, because as I mentioned, we usually get called in to say, hey, can you park your fire truck here if they do landscaping here, or, you know, do you like where the FDC is on this side of the building, or should we move it over there? This was a collaborative effort from day one. You know, it wasn't just a, you know, hey, we're doing this project, you know, any objections? You know, they had overseas experts, they had you know, some other subject matter experts in the room, you know, ready to assist us with any of the, you know, the technical and construction trade subject matter expertise on the project. So we were, you know, we had all the right people in the room on day one, and getting everybody in the room. I don't mean to sound too overly melodramatic about it, but having everyone in the room to kind of, you know, not sit there with arms folded, but actually roll up their sleeves, get to work, look at the plans and the scope, design, desires, and dreams of the project, and you know, having all that in the room, and everyone available to answer every question, was able to get this project launched immediately. So, and as I mentioned, it was the best collaboration, yeah, I've been a part of, and you know, I would take heed as on the Ascent project process, and you know, follow it in your jurisdictions if you're hoping to, you know, exceed, you know, any requirements for the variance process, or, you know, involve your municipal stakeholders in the project.
Excellent insights. Thanks to all of you. All right, this question is probably going to be more for our design team. It's related to the structural weight. Can you comment on the total mass of the structure compared to a similarly constructed or a similarly sized structure constructed out of concrete? Does the mass timber save on structural weight at all, or were we able to see reduced foundation sizes or any benefits like that in a structure like this?
Oh, yep. This is Jordan. Absolutely, no question that this structure is lighter than a concrete counterpart. And I sort of alluded to it with the actually having to sort of stage stress this because it was so light, and the fact that really it's not just the wood, but really most of the weight of the structure, maybe almost half of it, is really the gypcrete, the 2 to 2.5 inches of gypcrete topping slab on each floor. So absolutely, it's much lighter, and no question that that's going to have a savings in the foundations. And you know, it's a little tricky to compare because the gypcrete has a weight, and we have some other concrete elements at the base that maybe change things. But if you said somewhere around roughly half the weight of a structure, with sort of some give and take in either direction. But I think the other big savings that Jason alluded to during his presentation is sort of the timing to erect it. And now, depending on what market you're in, you know, larger cities, for example, like a Chicago or New York, where they can do PT on a, you know, 2, 3, 4 day cycle, you know, there might be arguments at whether or not the mass timber is any faster. But the one thing that maybe that doesn't take into consideration is sort of the work that people are able to do underneath the mass timber floors, and as Jason said, how clean the structure actually is, and the fact that there's much less shoring and just stuff, I'll say, construction equipment in the way. So this idea that not only are you sort of erecting the structure, but you're also sort of opening up the space below so that the trades, the MEP folks can actually sort of be building along with the structure has really a fair amount of potential time saving, depending on how the contractor lays out the project.
Excellent. All right. This one is another question for all of you. Can you talk about some of the specific discussions around the fire testing? How did you decide what to fire test specifically, and how, how did those conversations kind of go?
So this is Jason. The requirements of 1A construction is that our vertical structure meet a 3-hour rating and our horizontal structure meet a 2-hour rating. The first tests were actually done for the framework project in Oregon in 2016. And not unlike our process, that there was a public-private partnership in the testing. I think the University of Oregon was involved in those tests, as well as the same fire engineer that we used on the Ascent team, David Barrer of ARP. And so that test data was public and we had it, which is why we based our exposed connection on framework. It's very similar. They actually had a more elaborate connection because they have seismic considerations that we don't. So that test was done. The 3-hour fire test for the glulam columns was done by us, has been presented. And then the last actual test that was performed in March of 2020 was a loaded test of the CLT slab, because by then we had picked a manufacturer. The manufacturer was European, so their standards are a little different. So the final test was done in March of 2020, and it was more about testing the adhesives that hold the laminations together, because if there was some fear of the char layer basically delaminating, and then the panel becomes compromised. And so that test, the standard that test had to pass was called PRG 320, and again, that was more about the adhesives than anything else. So we did 2 tests. I don't know if that answers the question, but they were critical to prove that the building could perform as well as a 1A building, basically.
Yep, and the one thing I would add maybe to the column test, and the reason we did it for the 3 hours is that currently in NDS, the char rating method is limited to 2 hours if you just look it up by the letter of the law. But what is also important to note is that's not necessarily based on any previous testing stating that something happens at 2 hours. It was just simply a function of heavy timber, primarily before Ascent. There was no reason to ever have tested beyond 2 hours because you never needed beyond 2-hour rating. So that said, as I've said a couple times in different presentations, is that we never would have gone forward with this project had we had any concerns that this 3-hour column test wouldn't perform as we anticipated, sort of in line with the equations that are already in NDS. Just from a pure mechanics and material standpoint, it intuitively makes sense that the more char you have, the slower that rate of charring will occur as the wood insulates itself. But it was really more of a crossing T's, dotting I's type of situation where, because it was technically outside of the code, we needed to validate to everyone on the team that we were sort of still within the bounds of appropriate design.
And this is Eric. All the above that was just mentioned. I won't speak to the specifics of the test. Obviously, it burned as prescribed, but it was a great proof of concept for the city of Milwaukee to kind of see the proof of concept of these columns would be able to structurally hold up, after that what we consider an extremely advanced fire condition on these structural members. So. And one note, I guess maybe an appropriate time to insert this, but one of the things that scares a lot of firefighter folks is when you say the term sacrificial layer. Although that's industry vernacular for this type of testing, the after effects of fire and the structural integrity after a fire. I would definitely, when discussing, the proof of concept, the fire testing, the historic fire testing that's already been done and what's been done in Madison, and come up with I guess a better vernacular that explains. I mean, we all know what Type 4 construction and heavy timber does under fire conditions, but when you say the term sacrificial layer, that kind of denotes still that inherent weakness in there. And I looked at something like maybe inherent prescribed burn rate or burn layer or something like that, and then that'll kind of lead people to not develop that narrative that there's any weakness after a fire condition based on the design of that sacrificial layer as initially termed.
And to follow up on that, after some similar conversations with Chief Roden and Chief Lipsky, we've taken to calling it a protective layer, because that's what it is. But exactly. It sounds more positive.
Absolutely. And any urban firefighter that's been a fire in one of the legacy Type 4 buildings, they'll walk through a building after a fire and they're astonished at the inherent fire resistance that the charring actually does. So, but just using those terms in the room in front of a PowerPoint are very polarizing to fire service and fire protection folks. So just a word of advice, but Jason definitely nailed it in terms of the right vernacular.
Absolutely. All right. We've had several folks with questions related to the sourcing of the panels. Again, this might be more towards the design team, but can you talk about why you opted to source the panels from a European manufacturer as opposed to a North American manufacturer?
Sure, I can speak to that. So in 2019, 2020, there was not capacity in the United States to produce this much mass timber. That's changing. We have several plants open now. And basically our core and shell contractor, C.D. Smith, worked with Timber Lab, formerly Swinnerton Mass Timber, who had a global network of relationships with suppliers and frankly installers all over the world. So the procurement effort was basically a global effort, which primarily came down to producers in Canada, both in Quebec and in British Columbia, or producers in Europe. And frankly, it came down to cost, because this technology was sort of invented by the Austrians, or reinvented, if you will, in the 80s. They're just the most experienced with it, and surprised to learn that they were more cost effective, even inclusive of shipping. And then the final sort of decision metric for that was our clients preferred the aesthetic of the Austrian white spruce. But at the end of the day, it came down to cost.
All right, that's very interesting. Here's a question, Jordan. I think you're probably going to be the lead on this. We've had several folks inquiring about the lateral force resisting system. Some folks are asking, how are the CLTs connected to provide diaphragm action? And others are asking how did you handle the tie-in between the CLT panels and the concrete shear walls around the core?
Sure, yep. So a couple of questions there. The typical connections were just standard spline connections with a top spline panel about 6 inches wide, inch and a half thick, with just nominal screwing across it. That was our typical attachment. Then for tension at the perimeters, where we needed sort of cord forces we had to take across, we had some steel straps. Nothing too exotic, I would say. Luckily, we're not located in, say, California, somewhere that needed really high seismic with much higher loads. We were controlled by wind loading off of Lake Michigan. In terms of the connections into the core, again, pretty fairly simplistic. We had a steel angle, sort of a ledge angle, that we had left a gap and sort of coordinated with C.D. Smith and folks in terms of when that gap would be filled in. These channels also, or excuse me, these angles also were connected by the channels I sort of showed in one of my photos to allow sort of vertical flexibility as you go up the height. The theory being that, as this over time, the building wants to shorten or move differently between the steel and the steel, the concrete, and the mass timber, that we allowed the contractor some flexibility in the field of where these things located vertically. So that really being more of I'll say a construction means and methods, as opposed to sort of a pure structural, say, diaphragm force idea. But one of those things that we sort of had to consider, and as the team has mentioned multiple times, sort of this collaborative nature that, where normally you might just be focused on your single portion, being the structure, that the team sort of all had to understand a fundamental amount of fire engineering, a fundamental amount of sort of construction and how things are going to be built and fabricated and things of that nature. So really the goal of this, as you saw with some of these connectors as well, is to keep everything as simple as possible, just to make sure that we were providing sort of a robust design so that everyone was comfortable with it, but also that it was, simple to construct so that we would make sure that we were getting a high quality product in the field.
Awesome. All right. Jason, I believe it was you that had the slides that talked about the dew point and some adjustments that were made to ensure that the dew point was not occurring within the mass timber floor panels. Now that the building is complete, has any sort of verification or testing or other evaluation been done to evaluate if the dew point is occurring where you all had showed it to occur in your models?
That testing has not occurred to my knowledge, no.
All right. Quick question here for Eric. Was there any modification necessary for fire radio transmission within this building compared to other high-rise buildings?
No, interestingly, we have had to make some contingencies for other developments in the downtown area, but for the Ascent, we ran into no interference, no background interference in the design, structure, positioning of the building. So definitely lucky in that regard.
Okay. Were there any concerns related to the mass timber being exposed to the elements during construction? If it got rained on, or obviously snow could be a concern depending on the time of year in Milwaukee. Was that something that you all had to address as a design team?
That was more, yeah, short answer is yes, it was a concern. Slightly longer answer is that C.D. Smith, who ultimately erected the timber, had extra laborers on site to basically work to keep water off the deck, and especially any standing water. But the final sort of piece of that was, once, as Jordan referenced, because there's no real reshoring with the system, the other trades could follow very quickly. So once a floor was enclosed and ready, for instance, to get its gypcrete topping poured, we had to monitor, or rather the contractor had to monitor humidity very carefully to make sure that the space was desiccated enough to tolerate the additional moisture that's generated by curing gypcrete. So the short answer was, it did get rained on, it did get snowed on. The contractors worked to keep it as dry as possible and made sure that it was dry enough to receive finishes.
All right, great. Another question for probably Jason, related to the sound rating. Did you have a hard time achieving STC and IIC rating requirements with the floor assemblies in this structure?
We did. I think moving ahead, and we did hire an acoustical consultant that we worked with. We ultimately had to use not the originally planned flooring in the building just to achieve acceptable transmission levels. The STC is not the problem, but the IIC is a large problem. Moving ahead, we would basically do a more robust topping to help generate a little bit of mass, or rather more mass than than 2+ inches of gypcrete can provide, because the STC for a 5-ply CLT panel by itself is only 30. So you do need to build up an assembly to get acceptable, again, mostly IIC levels. Ultimately, to get an acceptable IIC, we had to do a luxury carpet tile above areas that had exposed timber, and then we used actually real porcelain tile above areas that were encapsulated.
Interesting. Okay. Was this one? I'll toss this one out to all of you, and whoever wants to take it can. Was there fire stopping between the column-to-column connections from floor to floor?
Yes, correct. There were, and so we had some, whether it was factory installed or they had done some on the site. As you can imagine, as Jason mentioned, this is built pretty precisely, down to the millimeter. But as things are tightened and put on site, gaps can occur. So typically, there's fire tape provided around the columns, such that that you can fill any gap. And the CV Smith team also had sort of say fire protection materials on site to make sure that with the direction of David Barber, that any gaps were being appropriately filled with fire rated materials.
Okay. Question for Eric. What considerations for fire safety during construction were taken for this structure?
Well, obviously, we had all the asks and wants that were, in the code, the construction debris. But the main thing for us was access to the building while it was under construction, and allowing our downtown fire companies the chance to come and, tour the building, see it under construction, see the utilities of the building going in. And, that was very valuable. I mean, if you ask the crane operator, what he saw, in addition to iron workers walking around, you'd see a lot of fire helmets, walking back and forth on the slabs as it was going up. And, obviously, everything was met again at day one in terms of, the NFPA 1314 standpipe and sprinkler system, requirements, and, the availability and usability of those while it was under construction. But, really, the main thing for us was we wanted it sealed, several floors down as it was being built, working standpipes, access, to get to upper floors if there was even a small rubbish fire or something like that. And that was, they were more than accommodating on all the above. And so we really had no concerns while it was under construction, even though it's at its most vulnerable at that stage in any building, especially mass timber. But we had full access to the building. We knew exactly what was operational, 24 hours a day, and we even had companies going through, all hours of the day and night, and there were no, there was a lot of site security. There was no, unauthorized personnel near the building. The site was wired pretty tight and clean as a whistle in terms of a construction site.
And one of the sort of things that we did just to provide more safety is we provided 2 separate laterals into the building. As Eric mentioned, the cores and the attendant steel stairs were always several floors above whatever timber deck was being installed. And one of the advantages of timber, given that level of pre-engineering and coordination that we just discussed, was that there is basically no hot work on the deck. The only hot work that really happened during construction inside the building was installing the fire stairs, but they were already inside, that rated core.
All right. Just going through the questions we've had. I think this, Jordan, you may have mentioned this in your presentation. So concrete and wood move differently. How was this compensated for especially at interfaces where the 2 materials are meeting?
Yep. Yeah, because that's a great question. That's really something that you really need to consider. And honestly, right now, the sort of, I'll say the research, that may be the one area that's lacking the most in tall mass timber. but it was really a function of, from an engineering standpoint, predicting what we thought from creep shrinkage, shortening, over time, what we anticipated the wood would do, and then trying to allow it to understand, assuming the concrete is going to have very little movement comparatively, and trying to make sure that through that shimming schedule I mentioned that, you know, it's very likely that during construction, we actually wanted some of these columns to be slightly above what you would call level, such that over time, as it moves, it'll move down closer to a level position. And then, you know, in a 50-year layout, it might be slightly below level. It's one of those interesting things that as a structural engineer, when you're doing a high-rise structure, regardless of mass timber, you know, the design team and the owner need to be aware that nothing is ever going to be level permanently. Things move over time. Just it's a sort of a fact of our industry and of construction. So making sure that you understand that and how you sort of best deal with that. In our case, as I mentioned, it was through a series of shims and a sort of robust surveying program, such that we were actually out on site with the CD Smith crew, and we got real-time feedback as to where these columns were vertically. So we could understand, you know, where our estimate's accurate. Is it moving in the way we think it is? Do we need to add shims? Do we need to remove shims? And then at the core, allowing sort of flexibility with those angles I mentioned with vertical slots to make sure that in the field, as CD is building this, they had the ability to sort of level things on the fly, I'll say, to sort of give us this flexibility that was sort of required.
All right, great answer. Quick question, not sure who wants to take it. Probably Jason. Was NFPA 13 used, or did you use 13R provisions?
And it was NFPA 13.
Okay. Question on.
Go
ahead.
Yeah,
Sorry.
it was NFPA 13. I don't think 13R would ever be allowed in any kind of high rise.
Agreed. I think you're
it.
correct on that. Yeah.
Yeah.
Question on the stair construction. What were the stairs made of?
As Jordan mentioned, the enclosure is a 2-hour concrete pour. The stairs themselves are steel diamond plate.
All right. It's starting to get into the speed round here. Short answers. Okay, I think a couple of you may have touched on this, talking about concealed spaces. I know we saw some pictures of the soffits over the kitchen. How were the inside surface of your concealed spaces protected?
So, as I think Jordan mentioned, we did apply for 3 variances, and one of them was to allow concealed spaces, which are normally not allowed in Type 4 construction. The fix for that, or the solution for that, was a lamination of Type X gyp on anything combustible inside those concealed spaces. So there is no combustible material exposed in those spaces.
Which is typical of what we would see in the new mass timber building types in the 2021 IBC as well, if they have concealed spaces.
Correct.
So, all right. This one's kind of a speculative question, so I don't necessarily expect anyone to commit an answer to be carved into stone, but obviously this is not a high seismic area, and we've addressed that it was a wind load controlled design. Do you think that a building like this would be possible in a high seismic area, or practical? And I know those possible and practical are 2 different questions.
Yep, but I would say, this is Jordan, I would say yes. The answer is yes. It wouldn't be built the same way, I'll say that, right? Particularly with the CLT diaphragms and some of the things we looked at. But to Jason's point also, he brought up that the connector we used for the beam to column connectors, the framework connector, was actually tested for a seismic zone. So absolutely. Would it be different? Absolutely. But I don't think there's any question that you could do something similar. It would just take sort of a more nuanced approach to certain connections and load paths. That's maybe it was a little different than what we had done here in Milwaukee.
Question on the connectors. I know you talked about some of the framework style connectors, as you called them. Were all of the connectors for the mass timber custom connectors, or were some of them considered off-the-shelf products?
So we looked into off-the-shelf products, and again, it came down to a couple things, one of them being cost. At the time that we were completing the design of Ascent, there were not any, at least to our knowledge, off-the-shelf products that were rated for 2 hours. So it was sort of almost a non-starter. There was one or two that were sort of in the process of getting a 2-hour rating. But once again, even those 2-hour ratings were somewhat limited in the capacity they could achieve at the time. So it really ended up being a lot of ours were sort of those more custom, sort of those framework connectors that were sort of engineered under sort of the design principles that the connection was originally tested to, unless of course that the connection and all the wood itself was encapsulated, in which case it was more sort of back to design principles of bearing and that sort of thing.
All right. What was the panel thickness that was used? I think one of you may have mentioned you had a 5-ply panel. Was that used across the entire structure?
Predominantly for the typical floors, yeah, it was a 5-ply, so a little under, I think, or maybe a little over, depending on what level the 7 inches. And then we did have at the amenity floors a thicker 7-ply panel, and then at the roof we had a smaller 3-ply panel. But generally speaking, predominantly throughout the building, you were dealing with the same 5-ply panel.
Okay. And can you comment on, I know you had mentioned the largest of the glulam columns was approximately 43 inches across. Can you comment on how many different size glulam columns you specified on this project? Did it change every floor?
Sure, I think we tried not to change necessarily every floor, just from a construction standpoint and a material procurement standpoint. But I do think we more or less had, and I can tell you, we had, as I pull up the drawings, 16 column types throughout the building. And then typically in some conditions, we would change it every floor, but every floor or two, we would change the sizes until we sort of, practically speaking, as Jason mentioned, once you get to the upper floors, there's sort of a minimum size you need, either just for the charring layer and or just to fit all the hardware required for the connectors. So yeah, I think the one you mentioned, we did have one that was approximately 40 inches. That was maybe a bit more of an anomaly. It had more to do with sort of sizing it more rectangular for a balcony opening. But we did have columns that got, routinely at the base on the order of 25 to 30 inches, sort of square.
Okay. What computer program did you all use for your pre-construction modeling?
I don't know what software CAD Makers uses, but all of our modeling was done in Revit.
All right. Here's a very engineer question. What units were used for design and fabrication? Was it done in metric or imperial?
The answer is both. I think a lot of them, though, so under sort of IBC and generally working with US unit, they were US units, but again, practically speaking, when looking at sort of the shop drawings, and because they were coming from Europe, there was a lot of millimeters as well. So that was it's a great point, that sort of part of the additional sort of consideration and due diligence on the project was making sure that we were there were no mishaps or conversion issues between them, but so it was really done with a combination of both.
Right. On that similar topic, were there any other issues or challenges that you occurred kind of trying to marry the European product with the North American standards?
The only thing that I could think of was, again, that additional final test that we had to do. I don't really recall much of anything else.
Yeah, from an engineering standpoint, it was definitely something that was front and center on our minds throughout the project. I think, as I mentioned during my part of the presentation, we really did multiple analyses. We did an NDS one, a Eurocode one, and then one that was a hybrid of the two, because as you can imagine, there is no direct correlation. It's not sort of like a load factor, like you multiply by 2 or divide by 1/2 for the capacity conversion. So it does take, a lot of coordination with the manufacturer, with the design team, with David Barber and his team, to make sure that everyone is sort of in agreement with sort of some of the conversions that are taking place, and the fact that really, particularly because of sort of the unique nature of Ascent, that we were making sure that we were providing a robust design that met all of the criteria of all three. So yeah, there was a bit more due diligence from an engineering standpoint to make sure that there is an appropriate conversion occurring between the two code types and methodologies.
Great. Well, we're approaching the half hour here, so I think we'll go ahead and close things out. Thank you so much to our panelists for a very engaging presentation and discussion on this landmark structure. We really appreciate your time on this. We appreciate the audience. Thank you for attending and for your questions. And Marcy, if you want to go ahead and take control of things, I'll give it over to you.
Thank you to Jason, Jordan, Eric, and thank you, Lori, for moderating. And again, thank you for having us. And this concludes the American Institute of Architects Continuing Education Program. Thank you so much for being with us, and have a great day.